Well, good afternoon. Thank you for joining. So, my name is Tom Davies from CBS, and today's webinar will be the third in the series focusing on FRED for physical optics. We did two previous webinars before the Christmas and New Year, and they're available on the website if you missed them. And the third one today is going to be just polarization effects in FRED, which I hope you find interesting. So about us, just briefly, for those of you who don't know us so well, CBS Europe is the main distributor for Photon Engineering's FRED optical engineering software. We sell and support FRED across Europe, excluding a few countries, and we have staff in 3 countries around the world, UK, Canada, and Japan, to support the FRED user base there. My name is Tom Davies, COO, and allegedly FRED expert. So just for those of you who are attending today who are not yet FRED users, just a very brief overview to what FRED is before we get started on the topic of the webinar. FRED is a comprehensive optomechanical systems design analysis tool. It is by default a non-sequential ray trace engine, but it also has sequential options. So it's really for virtual prototyping, rigorous optical mechanical analysis. It has an optimizer, and the highest version of FRED, called FRED MPC, has the ability to do the ray trace on the GPU for ultra high speed calculations. It is quite a general purpose optical engineering tool, so it's suitable for various items such as convenient coherent beam propagation, stray light analysis, imaging systems analysis, illumination system design, and general catch-all terms of virtual prototyping, tolerancing, fabrication, and testing. The topic of this webinar, though, is physical optics. So just a brief definition so we're all on the same page. Physical optics, or wave optics as it's sometimes known, is the branch of optics that deals with coherence, diffraction, interference, and polarization, and other phenomena for which the ray approximation of geometrical optics is not valid. It is the intermediate between geometrical optics, which completely ignores any wave effects, and the rigorous electromagnetic theory and quantum optics. So it's the middle ground there. And FRED is able to handle this using, keeping track of polarization effects, and also for coherent effects using the Gaussian beam decomposition algorithm, which I've talked about in previous webinars. So specifically in regards to polarization, let's just have a brief overview of what FRED can do and a couple of examples. And then I'll do a couple of live demos at the end of this webinar, and then leave it open for Q&A. So quite simply, if you want to model polarization effects in a FRED ray trace, quite simply, you just have to set it at the source. So here on the screen here, we see the user interface of FRED's source primitive dialog, where we have the default source types. And in this specific case, it's for a coherent plane wave. And on the right side here, we can switch it on to be polarized. And then we can define quite simply if it's linear or circular or elliptical, and the angle of the E field vector relative to the local x-axis. So in this case, because this is a simple user interface, the source can either be fully unpolarized or fully polarized. There's no partial polarization setting here in this simple interface. If you wanted a bit more flexibility in the options, then FRED's detailed source dialog, where we have many options for customizing the source, has a lot more options in regards to polarization. We switch it on to be polarized, and then we can set basically ellipticity, handedness, polarization angle to be explicitly defined or randomized as per our desire. So it gives us a bit more flexibility there. But essentially, that's all you need to do to ray trace and keep track of polarization. And then throughout the ray trace, FRED keeps track of the polarization vector and the changes as it interacts with coatings or wave plates and birefringent materials, things like that, so that at the end of the ray trace, we can plot various quantities. One of the most simple things we can do in Fred is plot the polarization spot diagram. This quite simply, as its name suggests, is a spot diagram, but actually draws the polarization ellipse for each ray. So for each individual ray, we get to see the polarization state. And here, 3 examples: circular polarization, some sort of random polarization, and then 45-degree linear polarization. But keep in mind, this is only for a really small number of rays. You wouldn't be able to do this for a ray trace of millions of rays, obviously. But it's good for general diagnostics of the ray trace and the model, understanding how the polarization changes from specific rays. In regards to waveplates and polarizers, there are 2 ways to do this in Fred. If you needed to model a polarizer or a waveplate, first of all, Fred has a very simple, ideal polarizer or waveplate coating. So this is something you would define as a coating and assign it to the surface, and that surface now becomes a perfect or ideal polarizer or waveplate. So here we have the user interface here of this coating setting, and where you can specify which type of object you want to set and put on the surface, such as a polarizer or a waveplate. And this essentially uses the Jones matrices for all the selections and uses those to calculate the polarization changes for the rays as they interact with that surface with that coating. So a quick and easy way to set up a polarizer or a waveplate coating. Alternatively, we could create a waveplate, for example, using a biofenial material, which is something that Fred can also handle in the ray trace engine. So just to clarify what birefringence is, it is essentially the decomposition of the light into 2 rays, which we call the ordinary and extraordinary ray, when it passes through certain crystal-like materials, where the E field vector sees 2 different refractive indices depending on its orientation. So quite simply, it's a schematic there demonstrating that. The Fred user interface allows you to define birefringent materials. So this is a material setting, which you then add to your plate or block object in the Fred window. And it can have 2 different refractive indices. In fact, this screenshot here, the refractive indices are the same, but obviously they would be different in a real birefringent material. So here, as a function of wavelength, we can create a list of refractive index values for the ordinary and extraordinary directions. And here we can specify the axes of the crystal vector. And then, for example, if we wanted to create a wave plate using a birefringent material, we need to ourselves work out the correct thickness so that we get the correct phase delay. So for example, for quartz material, I have a table of refractive index values for the ordinary and extraordinary directions for 3 different wavelengths. Pick the wavelength we want to operate at, solve this equation. If we want a half wave plate, we'd solve this equation for pi, a phase delay of pi. For a quarter wave plate, a phase delay of pi over 2. And here are just some results of that calculation there. So if I wanted to create a quarter wave plate at 532 nanometers, I'd be using this thickness here. And then I would know that it would act as a quarter wave plate, and in other words, rotate a linear polarization to a circular polarization, for example. So you would have to do this yourself, but it's quite a straightforward calculation. And obviously it depends on the wavelength involved and the material you're using. So another thing that Fred can do, which is really quite valuable, is if this is a coherent beam, a coherent source, and in this case here we have a coherent point source, like very high divergence angle hitting a screen close by. In this case, this is an E field vector 0 degrees relative to the x-axis, so essentially EY polarized. What Fred can do, though, is if you plot the coherent vector field analysis, instead of just a simple radiance or something like that, you actually have the ability to look at the individual EX, EY, EZ components. And that allows us to really understand the coherent field for each component there. And what I have here in the right-hand side of this slide here is obviously the EX, EY, EZ components. And I've got two different cases here. The top case here is the case you see here, where we've got 0 degrees relative to the x-axis. And you can see it's slight curvature here due to the high divergence, x component, z component. The row along the bottom here is what we think initially is the same source setting. We're actually, instead of 0 relative to x, this is actually 90 degrees relative to y. So, yeah, x polarized. I should have mentioned that at the start. I think I said y polarized by accident. So 90 degrees relative to y, you think should be the same thing, but for a diverging source, that isn't the case. You can see here the slightly different field profiles. So interesting that that's the case, and Fred allows you to analyze these things as well. I should point out, though, before you get too excited, the EY component and EZ component are much lower power values than the X component. I didn't put them on the same scale because these are very, very weak. I wanted to show the actual fields, but these are probably many orders of magnitude weaker than this. But it's interesting to see the form of the profile of the EX, EY, EZ components. And as I said, if this is a coherent source, in Fred, you can pop the coherent vector field and then switch between the components and have a look at this yourself, which I feel is quite valuable. And then a final topic I just want to mention before I do a couple of live demos. One quite convenient analysis that can be done for polarized fields to really quantify the polarization state of the field is something called Stokes analysis, or Stokes parameters, or Stokes vectors, sometimes they're called. They're very useful for problems where the light isn't completely one polarization. It allows you to understand, sort of a hybrid state. And quite simply, it is a way that we calculate these quantities here, which here I'm calling two things meaning the same thing. S0, S1, S2, S3 equals I, Q, U, V, just two different ways to say the same thing. And we calculate them such that once we calculate these individual quantities, basically the EX, EY, and so on, we can understand quite simply from the values obtained how much of the beam is in a certain state. For example, if the result of these equations are that we get 100% Q, in other words, Q is exactly the same as I, which is just the total power, it is linear polarization along the X direction. If it's minus Q, then it's linear along Y, and so on. And then same for U and V. U is a 45 degree, V is circular, plus V is right-handed, and minus V is left-handed. So it's a good way to sort of quantify a hybrid state of a polarized beam. Now, unfortunately, Fred doesn't have this option as a built-in analysis. So this is something that you typically do using a script, which Fred has a built-in version of BASIC that you can write these types of analyses yourself. So the way that this would be done, it's a little bit, I guess the issue is we have to do multiple calculations on the same model, so that if this is a huge calculation that ray traces after, like, it takes an hour to ray trace, it's less of an attractive option. But what we do here is just before our detector, we add a filter. So we add a surface just before the detector. We define the series of these ideal polarizer waveplate coatings, and we're going to switch them on and off one by one so that we can collect each individual quantities, and then we can do our own sums. So essentially, we're going to switch them off one by one, do the ray trace for each one, combine and display the results. So it actually requires 6 different scripts, 6 different ray traces in a loop to get the results we need. So obviously, as I said, not really suitable if you've got an hours-long ray trace calculation, but for simple models, it's a great thing to do. And this will be one of the live demos I do, so we can talk about it a bit more then. But quite simply, here I've added essentially a dummy surface in front of the detector, and I'm going to loop through my list of polarizers. So I've created polarizer surfaces and polarizer coatings, switch them on and off, do the ray trace, calculate the results, and we can produce these Stokes parameters and understand the actual state of the beam, which is quite valuable and I've used a few times before. Okay, so I'll switch over and do a live demo now. I'm going to do 2 demos. I think we've got enough time for 2. First thing I'm going to do is just talk about Biofenial Materials using a Maltese cross, and then we'll do a Stokes analysis example I just referenced. Okay, so this is a very simple model, as you can see. What we have here is a source right at this point here. It's a highly divergent source. Essentially, we're focusing away from minus 0.5 millimeters from the source plane. So it's really coming at quite high angle, and it's a coherent beam. So if I just switch off these 2 objects now by setting them to be not traceable, just do a very straightforward ray trace. Okay. And I can plot the coherent vector field. Okay, so that's an interesting pattern, but look at these numbers, they're tiny. So obviously, this is not an EX polarized source. Let's switch from the right-click menu to a Y component. Okay, these are more sensible numbers. So what we have here is a Y polarized source. Okay, and we can just confirm that in the source settings on the polarization tab. Linear, handedness exact 90 degrees relative to X, so it is Y polarized. Okay, that makes sense. So what we have here are 2 polarizers back to back. And when I say they're polarizers, not just because I named them such, what we have here is quite simply the materials folder. I've got a very basic, just essentially artificial birefringent material where I've got a slightly different refractive index here in one of the ordinaries, and I've got a very high absorption coefficient in one of those directions for the birefringent material. So essentially, it's going to absorb very quickly any polarized state that isn't aligned with the ordinary axis. That's just a very simple way to create a sort of polarizer. And then this material is assigned to these objects. And so I'm not using those ideal coatings. I'm actually using a birefringent material with a high absorption coefficient in the least desired direction. These polarizers are the same. All I've done is I've rotated the second one 90 degrees so that it's actually going to absorb the other axis. So what happens is we've got a diverging beam that's going to first absorb the EY polarization, and then it's going to absorb the EX polarization. And what we have left with at the end is essentially the what's called the Maltese cross image, which I'll show you. I'll show you first of all just in the irradiance. Quite simply, just a small amount of power left over, and this sort of cross picture in the center here is something that can be used to sort of help diagnose essentially the birefringent materials we're using or things like that. So this is the birefringent, this is the Maltese cross. Just these small components here don't get filtered out by the cross polarizers. And that was the irradiance. Let's see what the vector image has to hold. Probably similar in each component, but let's have a look. So this is the EX component. These sorts of power values, right click, EY component. So similar, but slightly different. And EZ, yeah. So quite similar, slightly different. So the irradiance is probably the most valuable thing we can look at right now. Okay. So that was Fred handling basically using the biofinial materials to create our own polarizers, as opposed to using the ideal polarizers, which is probably my favorite technique. And then second example I want to show you is the Stokes analysis that I just went through at the end of the example here. So again, quite a simple model. We just got a source coming through, and this is our detector here. What we have here is a very simple test case where the source itself is EX polarized. And we can check that ourselves. Let's just create the source plane, plot that polarization spot diagram. All right, there we have our rays EX polarized. So I'm just going to close off some previous windows so I get a few more tab space. Okay. And then what we have here is a quarter wave plate. So this will change the linear polarization to circular. So we know what to expect at this test case here at the detector. If I plot the spot diagram, it will be circular polarization. All right. So what we have here are a series of polarizers. I'll just show one of them. So I've got this, added the surface just before, each with their own ideal wave plate coatings on them. So I can calculate these Stokes parameters. And I do that by a script. And I'll just show you the script without explaining it too much. But you can see the sort of the quantity of script that's required. Quite simply, all we're doing is getting the list of polarizers from a certain location in the object tree. And then we just have this one big loop, not that big, but one loop here that will set the polarizer one by one, do the array trace, calculate the irradiance, and then store the irradiance result from the result into an array, which we've done at the end of the loop, we calculate the Stokes vectors, the Stokes parameters we talked about, and then we just display them in the output window. So thematically, it's quite straightforward to understand. Not too much code. Wouldn't take you too long to write this if you have a lot of experience with in Fred Basic. So if I run the script, I know the output's coming in the output window. I'm just going to make a little bit more space for it. Okay. So right click, run. You can see here the dummy plane switching on and off as we cycle through the list. And we can see here quite simply the results. Hopefully you can see that on your side of the webinar. What we've done here is actually calculated it in two different ways. We're using the average irradiance values and the maximum irradiance value, just to see if they vary a little bit. Now, the interesting thing here is I is the total power in the beam. So that's just a sort of calibration unit. Q is 0, U is 0. So all of the beam in this example here is basically negative V. Okay, so degree of polarization meaning this, this is 100% polarized, and it's in the negative V state, which if we go back to the webinar, negative V meaning it is essentially left-handed circular polarization. It's 100% left-handed circular polarization, which meets our expectation because we have a linear field going through a quarter wave plate, therefore it's circular polarization. So kind of like a test case. Using the maximum values here, the values are slightly different, but the end result is the same. It's 100% negative V, therefore 100% circular polarized. And just to check that ourselves with a polarization spot diagram. Oh, yeah, sorry, my mistake. Because we're going through a biofinial material, the ordinary and extraordinary rays are split up so that we can't actually see the circular. So we actually needed to use the Stokes analysis there. And that's one of the key points there, especially when using biofinial materials. Okay. So I hope those two examples made sense. If you're Fred users already and you'd like to have a look at these examples, let me know and I can send them out to you. And then just as we wrap up the 30-minute webinar here, just some place where you can get some more information. Our website, cbseu.com. We have some articles on the blog. And of course, you can email us for technical support. And also at the Photon Engineering knowledge base, there's a whole collection of articles there too, which are very useful to browse if you're hunting down the answer to a question or hunting down a script that does what you're hoping to do. So please use these avenues for support and information. And we'll finish there with a Q&A. So I think we have a couple of minutes for a Q&A. If you have any questions, please use the Zoom chat, and I'll do my best to answer them. And if you ask a tricky question and I can't answer, I'll do my best to research and get back to you. Okay, so there was a question that came in earlier in the webinar asking how to model partial coherence. That's a little bit tricky. I do have a good example for partial coherence. Wasn't really the topic of this webinar, but it's essentially similar to the Stokes analysis, where you have to do something in a script to get a sort of an understanding of the partial coherence. And I might actually make this the focus of a webinar in the future, because it's a difficult topic. And coherence generally in Fred, the settings are quite simply, it's fully coherent or fully not coherent. So partial coherence is a kind of a special case, but we do have an example where we do that. And certainly to the person who asked the question, I can send you we actually just have an article, a white paper about it. I can send you that and the model file just for you to look at. But I do think it's a topic that might be worth its own webinar in the future. So both of these examples I showed today used a coherent beam. There doesn't necessarily need to be a coherent case to keep track of polarization effects. We can model incoherent polarization effects as well. It doesn't have to be coherent as a prerequisite. So yes, the polarization options at the source are available and it's not a requirement that is a coherent source type. Then I'll leave it there. Thank you for attending. I hope it was useful. Of course, reach out if you have any questions or comments or would like to receive the example files I showed today. I'm happy to share them. And again, thank you for your time.